What's f of x?
So f of x is 2x squared plus 3x minus 8.
Okay, now think, okay, plus 3x minus 8. Okay, and what was g of x?
G of x is x plus 1.
Now, guys, I think, if I'm not mistaken, we did this one yesterday.
Oh, we did do this yesterday. Yeah.
Which is okay. Which is okay. We did this one, get a sense of what it means to do here. Tell me the other, I think I had another one there also. Example.
The next example?
Yeah, I think it may be on the same side there. What was the
That
other?
f of x is the square root of x.
There we go. Square root x. And g of x,
The square root of 2 minus x.
square root 2 minus x. Now, this is where we get right into some difficulty. We know how to form the composite. Composites will be easily composed, written. But the question that's going to come up today is, and Jonathan, you were asking what that capital D there meant. After you find it, they want down the domain of it. That's going to be, might be an issue. Caroline, before I jump into this, was there another one after this to do?
Example 3 is f of x is 2x plus 1 over x minus 1, and x cannot equal 1.
Okay.
And then g of x is x plus 1 over x minus 2, and x cannot equal 1.
Now, is that the last one where I'm asking for the composite? Okay. Right?
Yes, and then the
Okay, let's do this one, guys. Here we go. And she's going to help me. On the side here, more than likely, but she's going to correct me here, was asking to find the composite in this order, little circle, first.
Yes.
Okay. And guys, you know what this means? It means f of, by definition, g of x. So it says we're going to take g of x, place it into that f function. I should be using different colors here, which I think helps. But let's try it. G of x, of course, she gave you g of x as this. Square root 2 subtract x. And the composite, that's going to take f of that. Which says go back to your f function, as we've done way back in the past here. Go back to my f function, put that in, that's going to look strange. If I take this back to my f function and replace x by it, please guys, do I end up with something that looks like this? Is that the way the composite looks? Which looks really strange, a square root within a square root. That's the way it looks? So you get credit for that, that's the composite. I would prefer it written as, and maybe a student can tell me there's another way to express that, which might look a little better than that. It looks awkward. I would accept this though, that's what it means. Does anyone see another way to write that?
2 1/2.
Well, this inside here would be 2 minus x raised to the 1/2. Hang on now. The inside part, if you wish, could be written as the square root of 2 minus x, could be written like that. But also, is there a large square root around that?
4/3.
Yeah, which means you raise all that to what? 1/2 again. A square root within a square root. And therefore we end up with what? 1/4? 1/2 times 1/2? So this could be written as 2 subtract x. If you wish, and Stanford may ask you to do it, 1/4, which can be written as 4th root 2 minus x. I like that response. I like that simplified response. So 4th root 2 minus x. Now, Caroline, did I ask to find, after you find the answer, that's the answer for the composite, did I ask immediately what's the domain of that? Okay, now that could be an issue. Here we go. The domain of this composite, right like this guy. What do you say, Professor? You got the answer down here. You said it's 4th root 2 minus x. Now, the way I have it written is not a square root, but it's a 4th root. What might still apply here in an attempt to find the domain? What may still apply here as it did for a square root? Should I also consider that 2 minus x to be greater than or equal to 0? If I was doing a 4th root. If I were doing a 6th root, same thing. 8th root, same thing. So that tells me right quickly, one thing I can do is 2 subtract x must be that, for that 4th root makes sense. Something like a square root. I can solve this, Move that 2 over, divide by a negative, reverse my symbol. Guys, watch, make sure I do not mess up there. Right now we have x is less than or equal to 2. Is that true? Now watch carefully, because I did those examples on that handout for a reason. Okay. Jonathan, you were asking about, trying to get the domain on this. Here's the problem, issue. It may not be finished. That may be a part of this. Here's the issue, to find the complete domain. How did I get this answer to begin with? I placed this within my f function. If this one has a condition on it, I'd better also include that in this, because I could not have done all this if this has a condition on it. So guys, way back at the beginning, she gave me square root 2 minus x and square root x. Let me get the domains of those basic ones that she gave me. This domain of the f function, easily seen. Since it's a square root, it's going to be that. This domain of the g function, I know and you know for a square root that 2 subtract x must be that. Which I'll solve. The inequality. Divide by negative, reverse my symbol. And guys, looks like now I see the domain on the g function is x is less than or equal to 2. Is that true, guys? Did I make a mistake or not? Are we okay? Now, far model. To get this answer, we got the answer like this. To get it, I place this, where is it? This one right here. I place this in F. If there was an issue with this, I have to account for it. Thank goodness I went over to the side there and found the domain of this one that I put in, which was this, and it came out to be this. Does it match up this sign with what we thought was the domain? Do they match up? Yeah, so that's going to be my domain. Sometimes they don't match up, you've got to include something. That may come up here shortly. Right now, guys, this and this matches up. So it looks like we're in pretty good shape here. Next, Caroline, was it probably G, circle F?
Yes.
Okay, number 2. Let's do it. G, circle F of X. And guys, again, by definition, it means you got to do this. You got to place the f of x into the g. So go back to the g function, this function right here, and put inside of it, replace x by the f function. So it looks strange. Square root, where am I? Put f into g 2 minus, and see if you guys would agree with that. Is that the result if I place the f function into the g? It looks awkward as you know what, but that's the answer. Really awkward. But that's the composite. That's what they're asking to do. Put one function into another. No issue there. Give full credit. Now, I don't see any way to simplify this one, by the way. I need to simplify this one a little bit. I'm going to pour through. That one has to stay like it is. Now, here's the question. What is the domain on that answer? There was a domain on your final result there. Guys, if I look at my final result, for sure, I think every student in class would say, Professor, all this, I'll put it right here, all of that underneath that large square root, for any square root, to make sense, this part must be, and see if you guys will agree, that for a square root. So that will give me a start. I will try to solve this, guys. A negative radical x, let's move that 2 over. Divide by negative, reverse my inequality symbol. Do not let me make a mistake, I got that. Now what would you suggest at this point, because I got to solve for x? What might I do now? Square. Square both sides, got a square root, that's square. And I do, I'm going to end up with x is less or equal to 4. Hang on, we got that. Okay, what agree with that? That's the domain, direct domain from the answer, staring at me. Now how did that domain, how did that answer come about? That came about with me doing what? I'd place f into g. If f is messed up some way, I can use it. So was there a condition on f to begin with? And I think we said on f to begin with, where was it? Here's f. This must be true. So guess what we have to do? We have to say, sure, I'll accept that x is less or equal to 4, but professor, also to get to that point, you were using f, and there's a condition on f. So you got to add this, put it right here, also. Here's your complete domain. The first part came from me just recognizing the square root business. And then I have to ask myself, how did you form this answer to begin with? How did you get that answer, professor? I placed this into G. If there was a condition with F, I could not do my work. Was there a condition on F? There was a condition on F. Its domain was this. So you've got to put that in there to make sure you get a complete domain. Best expressed, both those together in interval notation for your domain, I would say 0 bracket up to what? 4 bracket. And there's your domain for the composite G circle F. This is going to get interesting. Now, if you get outside that domain, something should happen that I could not have done the work I did. Let me get outside the domain. Let's try something outside. I don't care what number you try. Let's try something outside 0 to 4. Guys, let's try 5. What's wrong with 5, Professor? Why will 5 not work? I'm going to try 5 here. If I try 5, this says first find f of 5. Well, I can do that. That's square root 5. Isn't it? And it says take that square root 5 into, and I'm going to show all the work here so you can see what's going on here. I'm trying 5, guys, just for an example. So let's try g of f of square root 5 f of x. Here. Close that up. Now I'm just checking at random a number outside this domain. I'm trying 5. Okay, put a 5 in here, guys. So it says g of f of 5. F of 5 first. And let's see what happens. I'm trying to 5. In this composite. Replace an x by 5. So something may happen. It says g of f of 5. If I go back to my original, here's the f function, put a 5 in, that becomes the square root 5. Now, can anyone tell you what that means now to continue? It's like two functions together, composite. Now it says what? G of square root 5, go back to your g function, which is this one, and put in a square root 5, and it would look like this for the g. 2 subtract square root 5. So what's wrong with me placing a 5? Or trying a 5, which is outside that domain? What's the problem? I tried 5. What's the issue? Why can't I try a 5? I tried. I got an answer. What's wrong with that answer? Oh boy. Oh boy. Jonathan, go for it.
Why didn't you consider that g of x needs to be less or equal to 2? Because if you tried 1,
I got you. I tried 5, because definitely you would agree that 5 is outside this. Is 5 outside this domain? If we accept this as my answer, from 0 to 4, is at 5 outside? I'm going to try one number outside. You can try 10, 6, as long as you're outside, or -1, -2, as long as you're outside. I tried 5. So I got this answer when I tried 5 for a composite. What's wrong with it? Well, square root 5 is 2 point something. So underneath there, you get 2, subtract 2 point something, you're going to get a negative result underneath the square root. And you cannot do a square root on a negative. We're not talking about imaginary numbers here. That's why you had better stay within that domain. Jonathan, class, if you tried something within this domain, it should work. I don't care what you try. If this says from 0 to 4, you want to try 1? Let's see if 1 would work. 5 did not work, I was outside. If I tried 1, it looks like this. We take G of, here we go, yep. G of f of 1. I'm trying a 1 here. F at 1, let's go to your function that she gave me way back here, f. Put a 1 in there. Square root 1 is 1. And then take that 1 from there into your g function, put it here, and you end up with this. Square root in my g function, 2 minus 1. Is that one doable? Is that one doable? So as long as you stay within that domain, it'll work. It's doable. I went outside, 5 did not. It should not. That's what we're doing. Now you're talking about madness? You gotta be careful on these. Caroline, what was the next one, guys? We got 1, 2 out of the way. What was the next composite?
G composite G.
Oh, G with G. Here we go. Which means, for a composite, this. That's its definition. G of x, if I look back at the original function she gave me, G of x was given to me as square root 2 minus x. I'll put that in right there. And so on the outside, you still have another G. Does it now go back and now put in that square root 2 minus x? Even if I do that, back to my G of x, it's going to look strange. Tell if that's what that might look like if I take this back to my G function and replace x by it, or substitute. What do you think it will look like?
Wait, you repeat that again?
Yeah, tell me what G of square root 2 minus x, which says lift square root 2 minus x out, take it back and put it in here. Put it back into my G function. What might it look like?
It would be 2 minus the square root of 2 minus x.
Welcome, Berkeley. Welcome, Berkeley. That's exactly what it would look like. A square root with a square root underneath it and a little bit more business going on there. Aiden, thank you so much. That's exactly what the composite looks like. That's exactly what it looks like. And I cannot do anything else with it, guys. Just leave it. My goodness, that's the answer. You get credit for that right there. Now, here comes an issue. Could be an issue. Not only do they want that answer, they want to know what's allowed for the x's to keep it defined. You got to find its domain. So, guys, with what he gave me that I just blocked off, that large square root that has that s underneath it, that large square root, would make no sense unless this, look at this, is this. Everyone agree? The large square root down there that has the answer would not make sense unless all that underneath it is greater or equal to 0. But you cannot take the square root of a negative. Now I gotta solve this. I'm gonna solve mine like this. I'm gonna move the 2 over. Interesting. Divide by negative or multiply by negative. We know what's going to happen here. This reverses, we get a 2. Now what would you suggest now, because I have to eventually solve for x? What might you attempt now? Square both sides? No problem. I'll get 2 subtract x on the left, less or equal to 4. Solve for x. Continue. Move that 2 over. If I move that 2 over, I guess I get less than or equal to, here we go, 2. Divide or multiply by negative, reverse my symbol, please, guys. I did a lot of work there. And we finally end up with that result. X is greater or equal to a negative 2. Okay. Here we go. Now, do I have the complete domain on this? Because you're dealing with 2 functions. You're placing one function into another. That's why this domain could be very, very tricky here. This much is okay so far, yes. Put a comma. And ask you this, how did we get that answer to begin with? We place this into the G function. Is there a restriction on this? Because if there is, I gotta be careful with it. Is there a restriction on the original square root 2 minus x, which I think was back here? What was the restriction back there to begin with? X had to be what? Less than or equal to 2. Right, put that on the side, right here. I'll use this. Because of this. This had a condition on it also. Guys, if you put those two together for a complete domain, please tell me in interval notation, x is greater or equal to a negative 2, and at the same time, x must be less than or equal to 2. What would that domain look like? Complete domain in interval notation. Is it bracket? Negative 2 up to 2. That's your domain on this crazy thing here. You get outside the domain, you try something outside, something will happen here. It's not gonna work. Wow, wow, wow. Caroline, was that the last one I asked you to do with those square roots? Now, I was only asking about bringing this one in. I don't think your textbook has this. I don't think it has this one. I thought, come on. Come on. Let's go ahead and do this one. We've done square roots and domains of square roots, and why not do it? We place one into the other, and then give the domain on that result. Okay, so I thought, yes, I'll bring it in. Now, I don't think this was on the handout, but let me do something with you. This is done, part 2. You guys, I hope you can see down here, let me know. If you're given this, say f of x is equal to 1 over x. G of x, let me use this red marker. G of x has been given to me as 2 over x plus 1. Now watch carefully, I'm closing this composite down. And they want you to find, or put those two functions together by considering this. F circle, and we'll close this down and use my colors here. G of x, which means you're taking f of g of x. Now this one's going to be, I think, a little easier than those square roots. That's why I'm bringing this in. Guys, to do this one, and I'm going to ask a few questions here. It says f of g of x. Well, g of x, the red function, right here, was given to me as, in the given, this. That's the inside part. It says now find f of that. That's what a composite's all about. Now can someone tell me what does that mean at this point? F of that red. What does it mean for you to do as a student to find the composite? Give me a description somewhere. What are you going to do now at this point to find the answer? What does it mean to do? And I mean, before you give me an answer, if this had said f of, and inside here, not that red, let's say it said f of 6. I guarantee you, every student in class will say, Professor, go back to your f function. F function here, I put in a 6. And you say 1/6, and we'd smile. You got it. If I ask you to take f of, and this red's missing, f of a -4, you say, Professor, it means go to the f function, replace x by -4. And you get -1/4. Same thinking though. It says now go back and put this in to the f function. If I do, it may look a little strange. It's going to look like this. Let's see if you guys will agree. Does it look like that? Which could be simplified easily as, you can clean it up. Hang on a second. We have all this correct so far? Okay. If I clean this up, guys, please tell me the final answer might look like. Can someone see it right now? What might that simplify into? scare me today. Today is Wednesday. Woo. Oh, it's gonna be faster. Okay. 1 divided by,
X plus one over two.
yeah, here we go. What? Oh, this marker's not gonna work. 1 divided by, is what it means. 1 divided by 2 over x plus 1. That means that. Which means 1 times, flip that over, x plus 1 over 2. So what's my final answer? X plus 1 over 2. That's my final answer? Okay. Now, is there a restriction, right now staring at that answer, is there a restriction that you can say Professor X can't be for sure on my domain here? X cannot be something or not, or is it open? May I replace X by any number I wish? The way it looks at this point, I'd say yes, right? But the reason I brought this in to close it down, how did I get to that point? I placed this function into it to get that. Was there a restriction on this one? Oh, I better point that out then. And what was the restriction on this one? X could not be equal to -1. That's my domain. Guarantee you, if I came up to you and was talking to you and discussing, and I said, I'm thinking about a function that looks like x plus 1 over 2. What's this domain? You said, Professor, everything, negative infinity through positive infinity, if that's a function. But then if I told you, no, I create this function by taking that function. So was there a restriction on this function? Yeah, x cannot be equal to -1. Aiden, what was that question?
Oh, no, you already answered.
Okay. Woo! Some of us, me included. You give me a single function, and you ask me to find the domain, sometimes just a single function may be a little demanding. Now I give you 2. Professor, could you give me 3? F of x, g of x, h of x? And put F, or F, circle G, circle H. I've seen that done. Am I going to do it here? No. We're going to have enough of an issue with 2. Okay, guys, does that look pretty good now? I thought that last one might make a little bit more sense than those square roots. Those square roots are messy. Okay, let me try before I leave the composite altogether. I'll stick with this one. Number 2. Here we go. Let's try to find, oh yeah, F with F. Which means for a composite, this. Look, dealing with the black function. Use the black marker here. This, of course, is 1 over x. That's given to me. So what I mean to do is take f of 1 over x. So go back to my f function, the black function, and replace x by 1 over x. So it's going to look like this. I'll take that back here and replace x by it. Guys, what was that cleaned up to? That's just x. That's just x. Now, if I came up to you and said, I'm thinking of a function, f of x is equal to x, now I'll be able to quickly say, Professor, every number works. You can replace x by any number you wish. If f of x equals x, it's no restriction. But on this one, how did I get that function? I've used another function. Was there a restriction on the function I was using to get to my answer? Yeah, x cannot be what? 0. I gotta point that out. Isn't that strange? There's the answer. You think, my goodness, everything works. You can replace x by anything you wish. Well, it's that composite, though, you got to take into consideration, how'd you get that? And there was a restriction. Wow, composites. Caroline, did I have anything else on composites on that handout? I don't think I did I? On just the composites.
You have one more question.
Oh, about the composites? Yeah, I got questions too.
Yeah.
Okay,
The-
hang on, let me take some questions. I thought the hands went up, which I love. I'll see that.
Switch back on this one where you play G,
that x cannot equal -1. I see that, but then the restriction of f of x or x can't.
Oh, I got you. You could approach it like that. Oh, yes. You said, Professor, I'm taking f of this. Was there another restriction? Oh, what was it? Was there another restriction on x to, f of x to begin with, where we said, what, x cannot be 0? Is that the part you're looking at?
Yeah.
Okay, so,
Oh.
okay, go ahead.
So would you consider x can't be?
Don't mind. Oh, I got you. I saw that question. Right here. The guy is good. This domain on the original f function is x cannot be equal to 0. That's exactly what we should be discussing here. And the red one, let me point out what the red was. This is what he wants. This domain is x cannot be equal to y. -1. Separate functions. Now guys, the way I set this up, and I asked you to place g of x into f, I just paid attention to the g of x. He said, Professor, should you also pay attention to the f? Tell me why not in this case. What am I going to get inside here? F of g of x, and all I'm concerned about is make sure that g of x is satisfied, x cannot be equal to a -1, and we got this answer here. By the way, tell me at this point, could x still be 0 here? We said up here, x could not be 0, but in my final answer, the way I approached it, could x still be 0? Make sense? The way, I know it's a little different, these composites can drive you nuts. Yes?
Would we be able to find range?
Oh, no. Good question. Only if we would somehow graph these. And they look at the graph and see how far up and down. No, they're gonna just ask us domain. Domain's gonna end up with a headache. Fine. What about?
If g was a different function, should we consider g not being 0?
Oh, you mean up here?
Yeah, g.
That's what, Oscar's asking about.
Oh,
Okay, he said, Professor, the way you found this composite, hold on just a second. Oh, I see what you guys are asking. Look at this. Number 3. Let me turn this around. I think I see what you're asking about. Suppose I do this. Here we go. Let's take the red function and compose it with the f, which means this. Beautiful question. Now, what does that mean? That means f of x, which was given as 1 over x, and you're taking it into the red function, the g function. And guys, if I take 1 over x into the g function, here we go. Let's make it right here. It's going to be 2 over, if I take that into my g function, I'll just use red. Here, 2 over, in place of x, I'm putting 1 over x. Look at this. Oh my goodness. Does g at 1, g of 1, g of 1 over x. Does it look like this if I take it back and put it in? If I put 1 over x into the g, into the red. Does it look like that? You guys at least agree with that. If I take that into the function. Now if I clean this one up, I know what you guys are asking about here. You're going to end up with 2 over, I'm going to put those two together with a common denominator. If I want to clean it up. A common denominator what? Suppose I ask you to combine those two terms on the bottom there with a common denominator. What common denominator would you use? This is understood to be over 1. To put them together, like fractions. What do you use? X. X. So if you multiply this one by x, oh my goodness, so you're going to end up with 1 plus x over x. And could I do more with it? What do you think the final answer would look like for that crazy composite? It says 2 is being divided by this. That's what it says. So can I do more with it? That means 2 times the reciprocal, flip this over. Now you have that. Which means I have what for an answer? 2x, 1 plus x. Wow. Wow, 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 Oscar. Mathematician back there. At this point, if that's the answer, tell the class what you see quickly as one restriction for sure on x. If I accept that red answer. Just basic on the answer you see in front of you. Is there a restriction on x? X cannot be a certain number or not? X cannot be a -1, for sure. Barbad, Oscar was asking the same, you guys are thinking along the same lines. How did I get to this though? I placed, I think, guess where was it? Did I place this? Was there a restriction on this? And I should take note of it. Was there a restriction on this that I used to get to this point? What was the restriction on 1 over x? X cannot be what? 0. Now that would come in here. You have one number from the answer itself, and then you're going to think, oh, no, how did that answer come about to begin with? So you got to go back and take a look at the other function that gave you that. Make sense? Whew. Good question. I'm glad you asked that. Okay. Caroline, I'm going to take off now. Guys, I did a little bit more on composites than I think your textbook did. I want you to get a sense of what it could be. Taking 2 composites and doing this and that. Now, here's where I think it comes into your calc class. Arena, Park, you can remind me. After all this, they're probably saying, is this going to do or help me in Math 7 when I finally get to Math 7, Professor? And that's what this course is supposed to do. Let me just point out real quickly. Mr. Park, Arena. And we'll give them a function. I may have done this on the handout. H of x. Caroline, check and see if I have h of x on the handout somewhere.
On the other page?
Yeah, maybe somewhere there. That's not all
I
clear.
have an H of X, yeah.
I do? What was an h of x?
It's
Oh.
like the one-to-one functions. I don't know if it's,
Is it a function, h of x?
yeah, there's like a few.
Okay, and what's it say? Is it a square root, something being raised to a power, or what?
Quantity 2x plus 3 to the 75th power.
Wait, 2x plus 3?
To the 75th power.
There you go. That's what I want. We'll close this down here shortly. Miriam? You're sitting there thinking, I know how Miriam thinks now. She says, Professor, no. You would not dare ask us to expand that thing out. 2x plus 3 times 2x plus 3 times 2x plus 3 times 2x plus 3, 75 times. Well, of course not. Of course not. All of a sudden you see this in the calc class. Mr. Park? Arena, do they ask you sometimes with something crazy like this, and you've got to split it up into 2 simpler functions and then deal with it? That's what this comes into. Now, can anyone tell me a processor we're using calc, they do not want students to leave it like this at the initial. They would prefer it written in terms of 2 other functions. We use different codes. 2 other functions that g of x. See that one also. They want 2 functions identified, guys. I'll just put on the side what we want. We want this, that when you say f of g, you get what she gave me from that handout there. Now, anyone take a look at the original function you're staring at in calc class, and they're saying, now break that down into 2 smaller functions. that when you put them together, will give you the original function she gave me. Does anyone have in mind what two smaller functions, f of x and g of x, might I use here? That when put together as a composite, would take you right back to the original. What do you think? Anyone? Everybody's shocked. Everybody's shocked. Miriam,
F of x equals x to the 75th.
thank you. And g of x would have to be
2x plus 3.
2x plus 3. And you form the composite, it will take you back like this. It will take you back to this. 2x plus 3 raised to the 75th. You split the function up into two smaller functions. Put back together, it takes you back to the original. Why do that? Because we're going to say, now do a calc technique. You'd much prefer to do a calc technique on 2x plus 3. X to the 75th, rather than the original. So we're going to ask you to please split it up, and then do the in parts. And then we'll use composites. That's a big part of what they're going to use it in calculus. Okay, guys, I think, Caroline, I don't have a handout right in front of me. Remind me what the next part is going to take me to. Where am I going?
In that same section with the h equals the f positive t, or
Yeah.
there's another one that's h of x equals the square root of x squared plus 1.
Hold on. H of x is equal to square root
Yeah,
of how much?
x squared plus 1.
X squared plus 1. And for some reason, I want you to break that down to two other functions whose composite put back together would give you that. Let's add this real quickly. I need an f of x and a g of x. That when you form a composite using those two, like this, you're going to end up with what she wants. Now, who has an idea what two smaller functions could I use? Or I mean, this would be a square root?
Yeah.
Okay, square root.
X plus 1.
And look at that. And it's telling me, Professor, this is x squared plus 1. If you form the composite, put x squared plus 1 into the red one, it takes you right back to this. And they consider in calculus these two to be simpler than the original, so deal with these two in that calc technique, rather than trying to do all this business in the original. Okay? Make sense? Just bring functions together. Okay, guys, I think that's what takes me to where I want to go. Jonathan?
The question like I have over here,
Sure.
like, what, d of g is x less than or equal to 2?
Right here?
Yeah, there, a little bit further over to the left, in red.
Oh, right here.
That one you don't consider?
Now, this was just domain of G. This is just this.
Yeah, I'm trying to figure out which one you care about, and which one you not care about.
Beautifully said. Beautifully said. That's what students always ask. The one you care about is the one you put in. The one inside here, this one that you put inside,
So
this
the
one.
domain of f, and then the domain of g, and then the domain of.
That's your answer.
Those are the only two
Those are the
domains you
only
worry
two.
about.
Those are the other two. Alright. Find your answer, look at your answer and say, I asked Oscar, on this one over here, well said, part where he says, here was the answer, I think, on this one. Immediately, you know x cannot be a -1.
Right.
Okay, so you're going to get that out of the way. And you think, well, wait now, how was this formed? This was formed by you placing f of x into, this is the inside part. Was there a restriction on it? Yes, back here somewhere, that. That's why I had to add a 0 to my domain.
But then you didn't really worry about what the domain of g itself.
That's what he was concerned about. No,
Oh.
no. It's that inside part that you're placing inside the function,
And then the end.
and then the end.
And then the product.
So those two put together is called a
Got
complete
it.
domain. Glad you asked them. Okay. Now, let me check and see. Yes. Now let's move away from composites and see what comes up next. Let me borrow yours. Right here. Let me borrow it Oh, yes, guys, here goes. 4.3, section 4.3, beautiful. No, 4.2, hang on, 4.2. This is where I have some notes also, besides what you have on that handout. I need all this organized today. Here we go. Yes. Erase all this. Lorraine, are you taking good notes for us? Because we are going to need some good notes today. Okay, guys, with that composite business done, you're going to have to practice some of this. Not what all this is about. Let me erase that much here. We're going to part 3. Here we go. Now, if the summer class moves too fast, you're saying, Professor, I was just getting comfortable with quadratic functions. I was just getting comfortable with polynomial functions. I'm not quite comfortable with rational functions, Professor, from yesterday with those asymptotes, but they're there. So we've done quadratic, polynomial, rational, Barbod, and the class is moving like that, so fast. Now they'll say, well, now I show the student how to find the inverse of a function. What? Professor, I'm going to move from f of x to the inverse of f of x. And I may not feel with this quick pace, I don't feel comfortable with f of x to begin with. I can write f of x, f, and close it with x. I feel good with that, just writing the notation. Are you telling me they're going to ask me to find now something called the inverse of that function? Well, that will make it easy on you. I don't think the textbook does this for you. If they're asking me to find the inverse of a function, guys, this involves this. I think this is a big help here. You're going to be interchanging the coordinates. We're interchanging the coordinates. Now, when I say coordinates, the x and y. Now, I brought in, before we jump in and try this, I think you're going to like this. It's going to be much better than composites, and forming composites like we just did. Guys, I'm going to have this. I'm going to have set A to get us started. I'm going to call set A a set of ordered pairs that contains coordinates, and show you what I mean here. I've got set A containing, in this case, these ordered pairs. -1, 2, 0, 3, 1, 4, and looks like that may be it. Oh no, I got another one here. 2, 5. Let me close that up. That's what you'd like to see on the exam. Wouldn't you? Would you like to see the function expressed just like ordered pairs, Professor? Please just write numbers for me. I can deal with numbers. But when you give me f of x equals x squared plus 3 over 2x minus 5, whoa! Please just give me numbers. Now first, is this a function? Does it satisfy the condition? Yes, there is no, when I pair these up, -1 paired up is 2. Is -1 paired up with anything else? No. 0 is paired up with 3, 1 is paired up with 4, 2 is paired with 5. So this represents a function. Now they want you to do this. And use the notation. They want you to take that and do this to it. A superscript of -1. Which means they want you to find the inverse. That's my notation for an inverse. So right here, guys, f superscript -1. says form the inverse. Anyone tell me though, you might be misled. If you see f raised to a -1, what might you think it could also mean? Someone tell me, yes.
It could be confused with 1 over the function.
And it can be confused with 1 over f. F to the -1 like a reciprocal. So we're gonna call it a superscript, not an exponent. So if a superscript of a negative, that means right there, guys, I have an inverse defined here. Yeah, okay. So f raised to a -1, inverse. Let's do it here. I'm gonna do this in red. And you're gonna help me out here. This is the x, this is the y. In my short description of what an inverse involves, you're supposed to interchange the coordinates. Can anyone take that original black function there for those 4 ordered pairs and really show me or tell me what it would look like if you interchange the coordinates? I'll help you out. The first one is this. You're just interchanging. This one becomes this. Of course, this one, when I interchange the x and y coordinates, you get that. And this becomes this. And there's A's inverse. Done. You just went through interchanging. No problem. I don't think. Now let's go back to the black function. Here we go. I'll make it real simple before I move on. The black function's domain is really simple here. The x the x's coordinates. -1, 0, 1, 2. That's my domain numbers for the black one. Range for the original, the y coordinates would be in the black function there, 2, 3, 4, 5. Done. Now if I jump down to the red, which is supposed to represent its inverse after I interchange, the domain on the red one, the x coordinates on the red, are these numbers. Done. The range on the red one would be -1, 0, 1, 2, looks like. And load that up. Was it 2 or 4? -1, 0, 1, yeah. Oh, what did I do here? On the red one, the domain 2, 3, 4, 5, we got it. -1, 0, just right off the board again, you see it. Now, does anyone see something happening between the domain and the range of the black and the domain and the range of the red? Did they interchange? So one quick conclusion is that the domain, which is going to be critical, make sure I find a marker that works for you. The domain of the inverse, like this, is equivalent to the range of the original. Also, the range of the inverse is equivalent to the domain of the original. Gotta keep that in mind. And that's what the black and the red ordered pairs show. It's just interchange. Now that said, let me go back. Does anyone have an idea, first before I leave this one, what rule do you think I had in mind when I expressed these 4 ordered pairs for the black function? Give me like an equation, or I'll write it as a function. What did I have in mind as I wrote these out? Because I did have something in mind as I wrote them out. Does anyone see maybe an equation or a rule there or a function that might express the black ones? It's called f of x. In other words, get from there to there to there to there. I've got a rule in my mind as I place those numbers. What's happening? X plus 3. The x coordinate plus 3 will give you the y coordinate. Make it consistent all the way down. If I look at the red and ask you the same thing, did I have a rule there for the red ones called g of x? Guys, who has in mind here a function for the red one?
X minus 3.
I heard x subtract 3. The x coordinate subtract 3, and you're going to end up with, as she gave you there, the red ones. So these do have rules to follow, or functions that you could express for the function and its inverse. That one's done. I'm going down here, and we're going to try some nice things here. We'll try one more set B. And set B is going to contain these ordered pairs. Before I move on any further here. I have, there we go, set B contains -2, 4. I have -1, 1, 0, 0, 2, 4. Close that up and make sure I have all that copied down correctly. Okay. I'd like to form this inverse for this function. I'll put it in red, and B's inverse, written like this with my notation, I need to go through and interchange. That's what the inverse means. If I interchange, guys, the first ordered pair now turned around looks like that. This one looks like that. This one stays the same. And turned around, this one looks like this. That's where everyone in class would agree with those. Just turn it around. Take a close look at it. Now I did what I said here. I'm interchanging. I did what I did. Here's the question. Watch carefully. Was the original set of ordered pairs representing a function? Was it a function to begin with, the black one? And in fact, many students probably could tell me the name I had in mind, or the function I had in mind for the black one. I think it's merely what? F of x is equal to x what? Squared? Now I go down to the G, the red. The red's not a function. And sometimes that can happen. Does anyone see G is not a function? So I have an issue. I tried to do as I said I was going to do here. I interchanged. And so when you give me something in red here, this I see repeats. 4 is paired up with -2. All of a sudden I have 4 being paired up with 2. That's impossible for a function. I don't want that to happen. I don't want that to happen. Now, can someone tell me, when we start leaving numbers, and we'll finally leave numbers and start looking at functions in terms of x, what might you look at in the original? The original's fine, it's a function. What might you tell me, wait, Professor, if it's a function initially, what are you going to look at in the initial to say, hold on though, it has no inverse? This one has no inverse. I ran into something that's not a function. Tell me what in the original though, black, that might alert you set to early on. Professor, that's okay there. But don't ask me to find the inverse, because I see something going on in the original that says, hold on, don't do it. It has no inverse. It's not going to work.
Repeating my value.
Which repeating value is it? For the y value. If you have a y value repeating back in your original function, forget it. That function has no inverse. Now, I got f of x equals x squared. That's a basic parabola. This may have a name, but it's not the inverse. It may have a name there to work with. You might be able to sit there and say, Professor, I see also a function that you can express for the red one down here for this one. I don't know, guys. Does anyone have in mind what that would look like if there is a name for the red ones? I know somehow maybe a square root's involved. Ooh, a negative out front? Square root x. Whoa. I'm just playing around with it. Let's see if it works. It may work. If I put a 4 in, Yeah, square root 4 is 2, prefix, I heard, a prefix is negative, that gives me a negative 2, that works there. Put a 1 in, I know square root 1 is 1, so do you, prefix negative, gives me a negative 1. 0 definitely works. Put a 4 in, oops,
Y squared equal to X.
whoops. We were so close till we reached that last word pair, it's not gonna work. I thought we had it. Now I'm hearing another student say, Professor, that's not gonna work, we tried. Now I think I'm hearing what? Y squared is equal to X. Wow. Let's see if that works. Square the Y and get the X. Here's my Y squared, you get 4. Here's the Y, negative 1 squared, you get 1. 0 squared, you get 0. 2 squared, you get 4. That works all the way across. But it's not a function. Has a name, but it's not a function. Now, Jonathan, the original function, real quickly, is a parabola. I gave you some ordered pairs. It looks like this. We know what a parabola looks like. If, just out of curiosity, does anyone think they know what the graph of y squared is equal to x? Not y is equal to x squared is turned around, the red one. What might the red one look like, do you think, if I should plot points, whatever I can do, and get a sketch? Okay, hang on down. Aiden?
I'd say it's a parabola, but it opens to the right instead of upward.
Oh, you tell me, okay, we just put it like this. Aiden, you're saying, Professor, I think that looks like that. The guys can try numbers. You can plot with ordered pairs, try a number. Aiden, I think you're correct. So y squared is equal to x, takes that shape. Y is equal to x squared that we're so accustomed to, takes that shape. Now, can someone tell me if you had the shapes in front of you? I'll put this right in front of me, I'll say, find the inverse of the function whose graph is staring at you. And I give you the graph. And I gave you a parabola. What would you quickly say and tell me what tells, or something on that, about that graph tells you, Professor, that function that graph represents has no inverse. Does anyone see anything about that parabola, the original function, as a graph that may tell you, stop, that function does not have an inverse? Everybody.
A horizontal line?
Thank you. That's something called a horizontal line test. So if I do this, guys, draw a horizontal line, not vertical line, horizontal. How many points of intersection would I get? 2. Do I get 2 points of intersection on this? I'm supposed to get only 1 to maintain a function. So this is called the horizontal line test. And it shows me in this case no. By the way, and keep in mind, here we go. Is the black graph itself, though, is it a function? Yeah, the black graph is a function. It passes the vertical line test. The original function is okay. But this shows me, when I do this, that what? It has no inverse. So don't even attempt to find the inverse if it does not pass the horizontal line test. Far about it. Here we go, on the side. You mentioned this. So all this function right here that looks something like maybe you're going to see on the quiz tonight. Oh my goodness. Looks like, oh, gotta be careful here. Okay, suppose you get that graph. That's a polynomial function that we're working with just recently. Does it have an inverse? No. No, it would not pass the horizontal line test. So some functions will pass the horizontal line test, you find the inverse. Some do not pass the horizontal line test, you leave it alone and say, yeah, Professor, it's a function, but it has no inverse. Don't attempt to find the inverse. It does not pass the horizontal line test. Okay guys, with all that said, I see my time here, part 4. I may refer back to the handout here, just let me see if I'm ready to refer back to it. Oh yeah, gotcha, yes. Now, I wrote myself a note. Woo! Your textbook does this for you. To ensure that a function does have an inverse, so you as a student would not bypass it and say, oh, it does not have an inverse, when actually it did have an inverse. The textbook does this. I love this description. They'll go back and say, well, professor, here we go. We'll give you a function. We'll make up one right quick, we got it. A little simple linear function. Does it have an inverse? If so, I'm going to attempt to find it. I'm hoping that it passes the horizontal line test. Now, I think every student in class can visualize this is going to graph into a straight line. Using the mx plus b form back from a previous class, right? Or x and y intercept. Do you think that straight line, no matter what it looks like, is it going to pass the horizontal line test? I think so. So it does have an inverse. Here's the description your book uses, which I'll start using. They will put on the side here to ensure that it does, that this function is a one-to-one function. If you see that description in your textbook, all they're doing is they're guaranteeing you there's an answer, there's an inverse. But it's got to be 1, 2, 1. By the way, let me, before I jump into this one, guys, this one down here, I think I just finished up one down here. What was it? This one down here is not a one-to-one function. Why not? Why? Just give me a description. Why might I say that's not a one-to-one function?
Because there's two of the same y value.
Yeah, because -2 is paired with what? 4, and all of a sudden, what does 2 do? It pairs up with the same number again. You can't have that. It's not a one-to-one function. If it's not a one-to-one function, forget it. There's no inverse. That's no way to do it. Your textbook is nice to you. He tells you, the algebra textbook, he tells you whether it's one-to-one to begin with. So if he says one-to-one, he's already saying, don't worry about it, student. It has an inverse. And then jump into it and find the inverse. Now, we got to try to find the inverse here. Number 1. I find the inverse of 4x subtract 3, and I will not list ordered pairs. So what's my first step, though, I did in terms of ordered pairs? I interchanged the coordinates. Anyone tell me this will look strange? No ordered pairs. What would this look like if I interchanged the coordinates in this? Vanessa?
And then be x equals 4y minus 2.
Love it. Any mathematicians in here? She says, Professor, you don't have to place the numbers for me. Just interchange. And then they want to do a second step. There are only 2 steps here to find the inverse. The second step is, after you do that, as she gave to me, solve for y. They want the y by itself. You guys, this one's easy. Just move the 3 over. Divide by 4. And you can leave it like this if you wish. And I'm making a little bit of a stronger statement. This is my inverse. There's my inverse. Done. Miriam. We'll check just a few things here to make some sense of what's going on with an inverse. Could you tell the class back in the original function, just out of curiosity, could you tell us, just for a little check here, give the class one ordered pair that you are guaranteed belongs to that black function?
1,
1,
1.
1. She says, Professor, if you replace x by 1 in what you gave me for 4x subtract 3, you get 1. That's okay. It's not going to quite illustrate what I want.
No.
Which is okay, though. Give me another one.
0, -3.
0, -3 looks pattern. That belongs. Now, if we are correct, if I interchange this one, for example, it becomes down here in the red, this. Which the inverse is supposed to do, interchange it. Now, Miriam, if I replace in my inverse down here, x by -3, interchange, -3 plus 3 gives me a what? 0, 0 divided by 4, will that give me a 0 there? So is that going to turn those ordered pairs around? It will. We try just one, it should turn all the ordered pairs around. Whoa, how many ordered pairs are there out there? I've got 32 students. I heard some classes are down to, low numbers. I've still got 32. And I won't keep all 32. No, I'm not gonna get down to 16 or 15 students. I want all 32 to pass. So if I start with my student number, Mr. Park, if I start with Mr. Park, say, Mr. Park, would you please, Miriam gave me this, Mr. Park, would you please give me another one, a different one than that? He could easily do it for me. Arena, I'd say, Arena, give me another ordered pair besides the two that Miriam gave me, and she could give me a different one. And I go all the way through all my class until I reach the end. Right? And I would check each one. Each one. Now, am I satisfied? How many ordered pairs are out there? Infinite. Infinite. So what we're saying is you had better come up with a plan here, Ramsey, to show that not only did Miriam's work, this interchanged. Let me throw in one more before I get my statement here. Let me throw in one more. Mr. Park. Guys, form another ordered pair that you know belongs to that original function, 4x subtract 3. I don't care what it looks like.
2 comma 5.
2 comma 5. So it's x by 2, 4 times 2 is 8, 8 subtract 3 is 5. The red one, if the red one's correct, when I interchange his ordered pair, like I did Miriam's, it down here turns into 5, 2. Interchange. If I put a 5 in here, 5 plus 3 is what, 8? 8 divided by 4 gives me what? 2. So his ordered pair, flipped around, works. Now, do we have time to check all of them? We're supposed to check all of them. How many of you guys say that are there out there? Infinite. You can't check all of them. So I need a little plan as to what can you do to verify that you did find the correct inverse and not have to take the time to start doing this business. And listing, then flip it around, bring it down here, test, and it starts testing. Oh my goodness, there's an infinite number of ordered pairs you're supposed to test. I've been in grad school where sometimes you get way out there and you find one that does not work. That was a shock to me. Certain problems, I never thought of that in my life. Some of the work I did in grad school, that math in grad school went crazy on us. I thought, wow, are you kidding? And 2 parallel lines finally being cut by a transversal? No, 2 parallel lines finally intersecting. Don't go there. Don't go there. Yeah, it's in a different type of geometry class. I thought, what? 2 parallel lines? They never meet. Oops. Let's think about it. So something like this. Oh, what was that?
I know, is that what spherical geometry?
No, I'll give you the name of it, what I think of it. It was way back, but I thought, wow. My math back in middle school and high school was so nice. If I had 2 parallel lines, I knew what 2 parallel lines did. They do not meet. I meet my professor in grad school. Oops. That was a different type of geometry. Not the type we took in high school. Okay, guys, here goes on the side here. We're going to take a break. Part 5. Now, I think this might take me back to the handout. Let me check if it is. Here. Caroline, help me out, please. Check, did I have something on the handout that had something to do with inverses? Well, I may have given you a
Property
fun.
functions or one-to-one functions?
Okay, one-to-one functions, and did I also finally, on the side there, sort of ask you to find the inverse? Did you have some?
Inverse for given one-to-one function.
Okay, got you. So given, this is a one-to-one function, and what was the function?
The first one,
Uh-huh.
it's kind of similar to the one you just did, it's f of x for x plus two.
Oh, x plus 2?
Yeah.
Oh, that was gonna be too easy.
You wanna do the next one?
Yeah, do the next one.
Okay, x squared plus four,
Hold on now.
comma, x is greater than or equal to 0.
Okay, here goes. Then we'll take a break here. I'm glad that she gave me from the handout, and I'm glad I placed it on the handout for you. If this were missing, there's no inverse. There's no inverse. That would grab into a parabola vertically shifted up forward. It would not pass the horizontal line test. Thank goodness she says, Professor, you have on the handout a restriction on that to make it one-to-one. To make it a one-to-one function, and therefore I can have an inverse. Okay, let's see what this looks like, and then we're gonna take a break here after all this is done here. Guys, I sketch this, easily sketched. Just a vertical shift up for transformation. And if I go up for right here, I think everyone in class would agree with me, it's merely my parent graph shifted, something like that. There's the graph. Is it true? Would that graph pass the horizontal line test? If I draw a horizontal line, would it have more than one point of intersection? So it does not pass the horizontal line test. So at this point, you would say no inverse and move on. No, she says, Professor, though, you put this on the side. What does this mean now to consider on my red graph when you see this restriction placed? So what does that mean? 80?
Everything to the left of.
Well, it says x is greater than. X is greater or equal to 0. Is it this side of the parabola or this side?
That side is removed,
The side to the right?
the side to the left. I mean, yeah, sorry.
No, hang on. So you're telling me, I think, fine, you tell me to erase that?
Yeah.
Okay, we got it. I just want that piece. That's satisfying x is greater than 0. Now, is that piece 1-1? Would it pass the horizontal line test? So now I can find the inverse. So I gotta be careful. I mean, very careful. But I can now find the inverse. Okay, guys, only 2 steps to find the inverse. First step, interchange the x and the y. So in other words, we'll go back and write the left-hand side as x, the right-hand side for the y. We'll do that first. The other step, last step, only 2 steps. First, interchange the x and the y from here to here, and now solve for y. They always want you to get the y by itself. And guys, if I do, be careful. I'll get that y squared all by itself, and then do what with it? Take a square root. Looks like, does it look like that? If it does, that's the inverse. If I have no mistake, this is that function's inverse that was given to me up here with that restriction. Now, Nima, to close out before we take a break, we'll all need a break here. Can you tell the class, this is my domain. They gave the domain to me. That's the x. I'm going to put it in integral notation. I think it looks a little bit better. Nima, can you tell the class what's the range on this function? The range function. The up and down. how would you describe the range?
Four to positive infinity.
Absolutely. Now close down. Now let's jump down to the inverse and you hit domain inverse. The domain of the inverse, there's my inverse, what do you think? The domain of the inverse, guys, will write like this. Anyway, what should the domain of the inverse be? Yes?
4 to infinity.
4 through infinity, hang on now. Was that not what he gave me for the range of this one? So did we say earlier the domain of the inverse should be the same as what? The range of the what? Original. Now let me ask you for the range of the inverse. Absolutely. Guys, the range of the inverse, and here's the inverse. Now, if I can't quite see it from square root x minus 4, what should the range of the inverse correspond with? The domain of the original function. So not too much thought here. Here's the domain of the original. So I have to say the range here, it's got to be in this one step here. It's got to be 0 through infinity. But this should be equivalent to the domain of the original. Is that making sense? You get it changed. We have a quiz tonight. The way you guys look, I hope you have enough energy. Whoa. I may have to start bringing in snacks. Sometimes I'll bring in snacks. No, Mr. Parker, Marina, remind me, we may have to bring in some snacks, especially Friday. Friday we'll have students just exhausted. Just exhausted. They're about to have someone out in the hallway waiting for them to escort them home Friday. And when they walk out, there'll be mom or dad or sister or whoever out there waiting for you. And when you walk out, they I don't even recognize you. What happened? Miriam's gonna say, Ramsey's test. I'm done. I'm finished. I need a break. Oh, thank goodness, Saturday and Sunday, I get the weekend. And what are you gonna do on the weekend, Mary? Sleep. That test exhausted me. That's right. Coming up. Okay, guys, take your 15-minute break.